Hi there. In this section we're going to look at a new type of limit called a limit at infinity. And we're going to look at some horizontal asymptotes. So let's jump right in and get started. So the idea here is if you have a function and you're interested what's happening way to the right or way to the left on the graph, you really can't rely on a graph as a proof, and tables can be misleading, so we need to figure out an algebra way to solve these things. And so we're interested in what's called the end behavior at the edges of the graphs. So we use the same notation that we used earlier in chapter 1 for limits, except instead of a number here we have infinity or negative infinity. But it's the same idea, and a lot of the same rules apply, as we'll see. So if the limit exists, then that number L is your horizontal asymptote. So there's many different kinds. You guys may have seen horizontal asymptotes in a algebra class or something. This is a little bit different, even though we're going to use a lot of the same techniques. In calculus, the functions that we do can take on a lot of different appearances. Later on in the class, we're going to see logarithmic functions and exponentials and some other things. So these rules hold for all of calculus. So as you move to the right, so the limit as x gets bigger of the function is L. So here as x gets bigger, we get closer to the line. Here as x gets bigger, we get closer to the line. And here we can go the other direction. As x gets smaller, closer to the line. As x gets smaller, closer to the line. So it doesn't matter what direction you're moving. As long as one of the limits exists, it's a horizontal asymptote. If both exist, they could be the same horizontal asymptote or they could be different. So again, we could try to use a table by plugging in numbers, and just looking at the table, it certainly looks like the limit of the function is 1, but that's not a proof. The graph certainly makes it look like the limit of this function is 1. But we need to develop some algebra methods to prove that this is in fact the limit. So now we get into the definition. It's very similar to our epsilon delta definition of limits earlier in the class. Essentially, if the function is getting closer to the limit as x gets larger, it just means that f can be made as close as you want it to L. So if you pick a number epsilon, then we can move far enough to the right to get that close or closer. Same thing here, moving to the left. If x is heading towards negative infinity, it just means that we're trying to get close to the limit. And if you move far enough to the left on the graph, that your function will get close enough to L. So here, we can move far enough to the right to get closer to L. Here, it just means we can move far enough to the left to get close to L. And the picture really tells you everything you need to know. So it's similar to the epsilon delta proofs, but it's not the same. We're not going to do any proofs using this limit. I'm going to prove one formula just to show you how it works. But generally speaking, these are more difficult proofs to do. And the graphical version is the way to think of it. So if we choose x large enough, just larger than some number, we can make the graph of f lie between the given horizontal lines, y equals L minus epsilon and y equals L plus epsilon. So we've shown that the picture really shows everything. So let's say you need to get within a certain tolerance, like epsilon is like 0.1 or something. On this graph, you can move far enough to the right so that every x value after that, the y value is between those boundaries. And if you make the boundaries smaller, we can move farther to the right. That's all it says. Again, the algebra on most of these gets pretty ugly, so we're not going to do a lot of work with this stuff. But looking at the graph, it should be believable. And so that's how we're going to define our horizontal asymptote. So if either of these limits exists, and it's some number, then there's a horizontal asymptote of the function at y equals that number. Also, we can have two different horizontal asymptotes. That's very important, because the limits could be the same on both on different sides. They could be the same, they could be different. If the limits are different on both sides, then you'll have two different horizontal asymptotes. But as you can see, you could have at most two horizontal asymptotes, because you're either going to the right or you're going to the left. So can a graph of a function intersect a vertical asymptote? Vertical asymptotes we saw earlier in the class. And I asked a question similar to part A on an earlier exam, and a lot of people missed it. And now the new thing we're looking at here is the horizontal asymptote. So let's see. Can we intersect a vertical asymptote? Can we intersect a horizontal asymptote? So it turns out the answer is yes to both. Here we have a vertical asymptote that the function intersects. Remember, an infinite discontinuity only needs to have discontinuity from one side, not both. So the function can, in fact, intersect its own vertical asymptote. And here, we have y equals 0 is our horizontal asymptote, and the function winds around and eventually settles down very close. So as we move to the right, the function gets closer and closer to x. So functions can intersect their own asymptotes. Watch for that on an exam. So now we want to prove both of these limits. So these are two, they might look like silly little limits, and you might think, oh, these are easy proofs. We could probably use the squeeze theorem or something. No, that's not what we're going to do. We're going to use the epsilon delta definition. I'm sorry, the epsilon definition we saw earlier. So to use the definition of a limit at infinity, the values of f need to be made arbitrarily close to 0 by finding a large enough value for x in the positive direction. So let's go back and look at this and see what this means. So if this is indeed the limit, then I can build a little boundary, epsilon, negative epsilon. And eventually, for any epsilon I pick, this function should get within those boundaries. So let's prove it. Okay. So here, this is the definition of our limit at infinity. So remember, it looks like the epsilon delta definition, right? And this is just a shorthand way of me writing negative epsilon is less than 1 over x is less than epsilon. That's the only reason I'm writing it this way. Just because epsilon has to be positive. But this is just a shorthand way to write it. Now I'm going to take the reciprocal of both sides, and that flips the direction of the inequality symbol whenever you do a reciprocal. There was one of these that I did in an earlier proof with the derivative of sine x. Now, this says the absolute value of x is greater than 1 over epsilon. Now, we know epsilon is positive. Now, because we're heading towards infinity, we also know x is positive, so I can drop that absolute value too. And now, for any value of epsilon greater than 0, there's some number x that's large enough to satisfy this inequality. Pick any number and say 1 divided by that number. You're going to get a number for x, and just pick x to be that number or something slightly larger. So there you go. That's how you use the proof. Most of them don't work out this nicely, and it's because of these inequalities. They flip a lot. But this one works out real nice. So that means that this limit is in fact 0. So that's part A. Part B, the proof of the other side is similar. You guys can try it on your own. Basically, it's the same thing, except when you get down to here, you don't want to drop the absolute value. In fact, you put a negative in front of it, and it works out very similarly. So both of these I will take as being proven without doing any more proofs today. So this limit is 0 and this limit is 0. So those are known facts from this point forward. And what we can do is we're going to combine that known fact with some limit laws that we saw in section 1.6. So some of the limit laws still work. In fact, all of them still work except numbers 9 and 10. We're going to cover these limit laws later on when we study L'Hopital's rule. So we're going to combine limit laws 6 and 11. If you don't remember what they are, just look them up. With the result from example 2 that we just got. And we're going to get a theorem. And so the theorem basically says that if r is some positive number that's rational, then the limit as x approaches infinity of 1 over x to that power is 0. So this is this is a strong result. So we're taking limit laws and something we just proved in example 2, and we're just combining everything. So this is for positive values of x. For negative values of x, as we go towards negative infinity, this is still true, except we need to check that these numbers are defined. You can't take even roots of negative numbers, and you can't take rational roots of negative numbers if the power has an even number in the denominator. So just make sure you're checking that. There could be some tricky things that happen. But from here on out, we're going to take this theorem as being a true statement based on other things we've proven, right? We proved some limit laws. We proved example 2 a second ago. So now, I'm not going to prove this theorem, but it's believable based on things we've already proven. If you want to prove it, you can. It's not hard to do. I just don't want to do it right now. Most of the time, students don't wish that I proved more stuff in class, but sometimes they do. So the way we're going to evaluate these limits at infinity is to divide the numerator and denominator by the highest power of x in the denominator. This is the same trick that you probably have seen in a college algebra class. It's the same exact stuff, except we need to use limit laws, so we have to show a little bit more work. All right, so let's keep moving. So let's go ahead and see what's going to happen here in example 3. So we're going to take these limits, and when we move towards infinity or negative infinity, we find the highest power of x in the denominator and we divide. So here it's going to be x, here it's going to be x cubed. So let's jump in and do part A. So I just divide everything by x. Then I cancel if I can. So here I'm going to be able to cancel an x. Here I'm going to be able to cancel an x. And then I use my limit laws and I push all the limits until they're right next to 1 divided by x to a power. As soon as I have them in this form, I can use the theorem. We know this limit. We've seen that before. We know this limit because even if you've never seen this exact thing before, the limit laws that we had in 1.6 still apply unless it's 9 or 10, and you won't have to deal with that. So we know this limit. This is 3. This is going to be 2. This is a 2 because I just pushed the limit all the way in. Now we can use the theorem that says both of these are 0. So 3 minus 2 times 0 over 2 plus 0 is 3/2. So that's our answer. Some of you might know different ways to do this problem. If this is on a test, you have to show at least this much work. You're allowed to show more if you want, of course, but a minimum of this much work. You can't use college algebra methods to solve a problem in a calculus class. All right, now for part B, it's similar, except we have this function here. This time, x cubed is the largest number in the denominator, so we're going to divide everything by x cubed. Notice we're going towards negative infinity, but that doesn't matter, as we're going to see. Simplify what you can. So here we have an x squared and an x cubed. That simplifies to 1 over x. Here we have an x and an x cubed. That simplifies to 1 over x squared. X cubed over x cubed simplifies to 1. So simplify where possible. Use the limit laws. Use the theorem. anything that is 1 over x to any power, positive or negative infinity, as long as that number exists, it's 0. 0 minus 0 over 1 minus 0 minus 0 is 0. So, not too hard. It's just a lot of algebra, and you have to keep track of some stuff. Okay, now let's see what else we can do. So here's a little algebra reminder. This is a fact that a lot of people forget about, so I always go over it. So the square root of x squared is absolute value of x. So if we're coming in from the positive direction, we can simplify that to x. No big deal. But if we're coming in from the negative direction, so if we're like heading, in the negative direction, look at the definition. The square root of x squared is actually negative x. So this is going to come up a lot. Maybe not on the homework, but certainly in future classes, and definitely, well, maybe not definitely an exam, but it's certainly a possibility. So a lot of people forget this, but it's easy to check. Try plugging in a negative number and just looking at what happens, and you'll see that it's true. So you are responsible for this algebra fact. Most people are fine with this positive one. But if it's a negative infinity, you have to keep track of it. So the notation, if we say that the limit as x approaches infinity of f of x equals infinity, that just means the y values get large. So this is actually the exact same notation from chapter 1. So I'm not going to make a big deal out of this. This equals infinity on the right of the limit has the same meaning. It doesn't have to be a vertical asymptote. It just means that the values of the function keep growing. Now, sometimes you'll get a limit in one of these things that's called an indeterminate form. You guys have seen a lot of 0 divided by 0 in this class so far. We're going to start to see ones that look like these now that we have infinities. And maybe you've seen an infinity divided by infinity, I'm not sure. So anytime a limit appears in one of these forms, so the ones we're going to see the most in this section are these four. You'll see these three later on in the class. Well, limit laws don't work if the limit does not exist or is in an indeterminate form. So you always have to check that the limit exists, and you have to check that it's not a division by 0 indeterminate form. Now we have to deal with what happens if we have infinity minus infinity or infinity times 0. So so there's a couple things going on here. One of them is that you need to recognize the form, but none of these things exist as real numbers that can be simplified in math. These are the 7 ways that you can combine functions together or numbers together. Infinity is not a number, but let's say functions and or numbers. And you don't want to write down something that is like a false statement or a does not exist. So whenever you see this, it doesn't mean that this does not exist. It just means we don't know what the answer is. So the way to get around that is just say it's an indeterminate form. So recognize the form, write down what the form is, and then you can begin to solve it using some methods that we've either already seen or are going to learn here in a second. So for example, if we have 2 individual limits that equal infinity, fine, great, we know what this means. But what does it mean to divide them? Can we say, well, it's just infinity divided by infinity? Not really, because that is indeterminate and doesn't mean anything. Instead, we just says it has this form that we can work on. So we'll see how that goes here in a little bit. So here we have 2 problems, both of which have indeterminate forms. We have to figure out the form and then evaluate the limit. So for the first one, let's say you just want to plug in negative infinity. Well, all kinds of weird stuff happens if you try that, right? Infinity is not a number, so we end up with this like nonsense arithmetic. But you can see that if you were to plug in negative infinity here, it would like represent a very large negative number. And just think of it that way. It's just a very large negative number. What does this mean? Well, this is a very large negative number squared, which is a very large positive number, minus a very large negative number. But this number is still a lot bigger than this number because this is squared and this isn't. So when we take the square root, this number is really what we're taking the square root of. So we have negative infinity squared. This is so much bigger than this that we can basically ignore this. So we end up with square root of infinity squared, which is just infinity. So this has the indeterminate form infinity minus infinity. Does that mean that we're done? Does that mean that it's 0 because those are the same number? Or maybe this first number is bigger. This infinity number is bigger. Or maybe this negative infinity number is bigger. What if we don't know? So the problems you're going to see, you can always deal with them by just following some algebra rules. But if you graph this function and you look in the negative infinity direction, it certainly looks like the function is approaching -1. So now that we know what the answer should be, let's see if we can use algebra to solve it. Right, there's your horizontal asymptote. Sure looks like it's getting closer to -1. So what we're going to do is multiply through by the conjugate. You guys have seen this trick before, and then we're going to simplify it. After you FOIL the top, and then you'll have x squared minus x squared, and then don't forget it's a -2x. Now we're left in this situation. Notice that our indeterminate form has changed. It was infinity minus infinity. What is it now? Plug in negative infinity here, positive infinity. Here we have negative infinity minus a very large infinity. So we're going to have negative infinity divided by, positive infinity divided by negative infinity. It's still an indeterminate form, so we need to keep going. And you just keep working on it until you can solve it. So this looks like a rational function, or it's closer to one. It's an algebraic function. So what I want to do is look for the highest power in the denominator again. Here's an x. And then here, what's the highest power here? You might be tempted to think it's x squared. But we have a big square root on the outside. So the square root of x squared is either x or -x because of the definition. So either way, it's x to the first power. It's either positive or negative. It doesn't matter which one you divide by, so I just divided by x, and that's the highest power. So, and then I want to push these limits through, but I'm only allowed to push limits through if the individual limits exist, and I don't know if this limit exists yet. I can see that this is going to cancel and turn into a number. Okay, this is going to cancel and turn into a number, so I can push that limit inside to there. I don't know what I can do here yet. So here's the trick. We want to bring this x into this radical. But that means this x has to be inside a radical as well. We can't combine terms unless they're the same power or the same base. Here, they're not the same base because this whole thing is the base. So we have to make it the same power. So I have to write this as square root of x. But when I put a square root on this thing, I need to keep the value the same. So I need to square this and then put it inside a square root. But because x is negative, when I replace x with the square root of x squared, it has to be negative. I have to flip the sign. If you're confused about this, go look back a few slides ago when I explained this. You must understand this because it comes up a lot. Maybe not a lot in this class, but certainly in future classes. So when your x is negative, if you see a square root in there, got to flip the sign. So here's where we had to do the sign flip, right here. So here's the last thing on the previous slide. Now, I need to get this x inside the radical, so I need it to have its own square root. I need it to have its own radical. But I can't just replace x with square root of x squared because x is negative. I need to replace it with this negative square root of x squared. So this is just a simple arithmetic substitution. Now I have two negatives, which become positive. And then I can just divide this up inside because the power is the same. So now I can distribute that inside, okay? So the radical goes away because the whole thing is in a big radical now. This works for all powers that match, okay? Now I can start canceling and I see all the limits exist. When I cancel this, I get -2. When I cancel this, I get 1. When I cancel this, I get 1. When I cancel this, I get, well, it's 2 over x. 2 over x exists. The limit exists. Now I can use the limit laws and push the limits all the way through. So I'm using all of these limit laws. That's a bunch. Now I use the theorem, which allows this to become 0. I evaluate this, which is just some arithmetic, and it's -1. And that's what we thought the answer was going to be to begin with. Looking at the graph, it sure looked like it was -1, and it turns out it is. So I know this is a very complicated problem. In fact, from an algebra standpoint, it's probably the hardest problem we do all semester, something like this. So work on these on the homework and let me know if you have questions. There's one more to go, B. So this limit is x approaches infinity of x sine of 1 over x. So you might draw a graph, and you'd be surprised. You might say, well, that doesn't look like what I thought it was going to look like. So let's see what's happening here. So if we decide to plug in infinity, let's say everywhere we see x, we plug in infinity. Again, guys, these are not numbers. And it's actually a best practices thing that I'm not supposed to write anything down that is a false statement or it does not exist. But I know that you're going to do it anyway, so at least I'm trying to guide your thought process, right? Infinity times sine of 1 over infinity. I don't know what that is. But remember, we're doing limits, so just the idea is that there's limits going on. 1 over infinity does exist. That's 0. But sine of 0 is 0. Oh man, now we have infinity times 0. So this is this indeterminate form. Whenever you have an indeterminate form, it means it cannot be solved as is. We're going to have to use a different technique. Can't use a graph, can't use a table. We need a different technique. And if you look at the graph, it sure looks like this limit should be 1. So I just want to point something out, guys. In the last example, we just got infinity minus infinity is -1, and now we're getting infinity times 0 is 1. Anytime a function is in one of those forms, we don't know what the answer is. Okay? And so if the true-false question says, this is infinity or this is 0, it is not true that anything times 0 is 0 when you're talking about limits. It's only when you're talking about numbers. All right, well, let's see if we can do some algebra to prove that this is, in fact, 1. So it turns out this is an example of a problem that looks hard but isn't. So I know we just got done doing a really hard problem. This one looks hard, but it's not too bad. So the first thing we do is we rewrite x as 1 over x, right? So it's sort of a reciprocal of a reciprocal. Some of you might recognize right away that this looks kind of like that limit we saw in section 2.4. Now I'm going to make the substitution. Theta is 1 over x. That means theta goes to 0 as x goes to infinity. So I can replace 1 over x with infinity, or with theta, 1 over x with theta, and x goes to infinity with theta goes to 0. Turns out that's exactly 1. And that's the end of the problem. So not a really tough one. All right, guys. Well, that's it for this session. There's a lot of up and down stuff on the homework. I would recommend taking some time to go through the problems in here first for the algebra. You don't have a ton of homework in this section, but make sure that you can do the problems that we just went over. So if you have any questions, shoot me an email or post on the discussion board. And until next video, I will see you guys later. Bye-bye now.